with our series, and we're creating polynomials off of those series, we're always interested in how accurate are the polynomials that we're actually creating. Okay, because remember, our series is an infinite number of terms, and a polynomial is just a certain amount of those terms. So once we stop looking at all the terms and we only look at the first 5, 10, 15, 20 terms, whatever it happens to be, we no longer have an exact value, we have an approximation of our actual function. So if we're dealing with an alternating series, there's one type of quick way that we can figure out how accurate our polynomial happens to be. All right, there's actually two errors that we're going to look at. One is Lagrange and the other is the alternating series error. And this video is about the alternating series error. So again, the idea is, well, if we have an alternating series, how far off is our approximation from the actual value of the function? Okay. And the easiest way to look at this is to start with just a nice geometric series. Okay, so if we take, for example, -1/2 to the nth power. Okay, we know that this is a geometric series because we get each preceding term by just multiplying by -1/2. So our first term is when n is equal to 0. All right, and if n is 0, then we have it -1/2 to the 0 power, which is 1. Anything to the 0 power is 1. And then if n bumps up to 1, now we have -1/2 to the first power. So that's -1/2, so we end up having 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16. We have an alternating series. Now because this series is geometric, we can actually figure out what the sum of the series happens to be. The first term is 1, so that goes in the numerator of our formula. And our common ratio is -1/2. So we do 1 minus -1/2, or as you can see there, 1 plus 1/2 in the denominator. 1 plus 1/2 is 3/2. 1 divided by 3/2 is the same thing as multiplying by the reciprocal. It's 2/3. So our sum of all of these numbers, remember this is going on forever, will be 2/3. All right. Now, if we're interested in like, well, how accurate is this? Let's say that we didn't have an alternating series which alternates, which grows geometrically. If that's the situation, it's not as easy to figure out how far off we are. Right? But let's use the one that we know about to see how far off we are. Right? And what I mean by that is, let's look at the partial sums. Right? We have no value whatsoever. If we haven't added any of the terms, we start with nothing. So we're right here on a good old-fashioned number line, all right, with 0, 1, 2's way over here, 3, -1 this way, -2. You get the idea. It's just an old-fashioned number line, but we're focusing on the region between 0 and 1. So if we add no terms whatsoever to our series, we have 0 sum at the moment. Right? Once we bring in the first term, our first term is 1, so 0 plus 1 is 1. So that means that we jump all the way over here to 1. Okay, and that's after one term. Now after the second term, all right, well, let's bring in the second term. The second term is -1/2, so we have 1 minus 1/2, which obviously is 1/2. So that drops us back to right about there at 0.5. Okay, and then we bring in the third term, which is 1/4. So now, oops, that should say 1/4 right there. So that shouldn't. I have the wrong numbers. My bad. So we're looking at 3/4 here. All right, so that's going to jump us ahead to where 3/4 happens to be. All right, this is 1/2. Right? And then our next term is going to bring us back this way a little bit. And then our next term is going to bring us up this way a little bit. And each time we get closer and closer and closer. Where's the ultimate spot? Right there. What's that value? It's 2/3. All right. But the first time that we added a number, we went too far. The next time we subtracted a number, again, we went too far. The third time we added a number, it took us too far. Then we subtracted, it took us too far. We always go too far when we bring in the next term. That's the secret to the alternating series error bound. Whatever the next term is, that's going to be the error bound because it's always going to go too far. So the actual answer will be just a little bit closer.